to welcome Sanjay G from Carnegie Mellon. He'll be talking about End System Multicast. Welcome.
Thank you, Ray. So good afternoon, everyone. So the problem that has been motivating a lot of research in the networking community is this notion of supporting broadcasting and conferencing applications. And here we are talking about ubiquitous, which means anyone on the internet should be able to do this. Maybe you have a lecture and you have students over the internet, or perhaps it's like a TV station of India which you're doing in North America. Right? We're talking of high bandwidth applications with tens to thousands of participating members. Here is a very quick summary of what this talk is about. I'm going to first argue that the internet lacks support for such applications. I'll argue that IP Multicast has not delivered. My research has been arguing for an alternate architecture, which is an end system overlay based architecture. I've been exploring some issues in the design of protocols with this framework, and this forms a key component of a fully deployed prototype. Let's think of the naive way of doing this, right? So I have a source here at Rutgers. I have recipients scattered around the internet. You have one copy of the packet go through to each receiver, and you have a lot of redundancy and links close to the source, and many copies of the packet traversing costly transcontinental links. Clearly, this is not desirable. In 1989, Steve Deering, in a seminal work, proposed an architecture called IP Multicast. The idea here is you change these routers to make them smart so they can split packets and forward them along multiple interfaces. Right? And from a performance perspective, this is actually great because there's no redundancy and so on. But what has happened here is you've made these routers smart. It's a very key decision that has been made. What's the significance of this decision? Traditionally, the internet has been designed with the philosophy that you want to keep your end systems as smart, you want to keep your routers as smart as possible, and routers as dumb as possible, and minimal functionality as possible. Right? And if you've seen the hourglass architecture, generally there's a thin waist in the IP layer, which means you want to keep the IP layer simple. The significance here is IP Multicast was one of those first decisions where you decided to change the router functionality. And a consequence of this is routers need to maintain state for every single multicast group, which complicates several issues related to scaling of these architectures. The second concern is fundamentally in the networking field. It's very hard to change networking infrastructure, what's called the ossification of the internet. Right? And it has been very difficult to deploy IP Multicast, especially on an inter-domain level. A third question is, what IP Multicast provides for you is a best effort service. Right? You send packets, the receiver may get it. But what applications want is some high-level functionality. So let's say you have a heterogeneous set of receivers with very diverse capabilities. The question is, how do you sort of deliver data to all these receivers using this IP Multicast abstraction? So since 1989, there's been a lot of great research in this field. Several publications, work which has won a dissertation award, lots of RFCs. For those of you familiar with it, a very large-scale experimental network called the M-Bone. But in spite of all this, the problems have remained unresolved. And the question that I and Yanghua began asking was it fundamentally the wrong decision to place multicast functionality in routers? So what we instead decided was to explore an alternative architecture for this that we have termed End System Multicast. The idea here is you retain the same semantics of routers today. There's no change to them. Instead, you construct an overlay tree among the participating members. Now, this figure shows you a virtual overlay that you might construct, right? So, Rutgers forwards data to a participant at Stanford, who forwards data to Berkeley, and so on. Now, these colors show you how it maps onto the underlying network. So, the path from Rutgers to Stanford would actually be something like this in the underlying internet. Right? Now, what's nice about this? First, your routers do not maintain per group state. Second, quick to deploy. There's no change in infrastructure. But finally, you also have, it's much easier to support high-level functionality. To see this, let's consider an overlay tree like this, right? And now the key is you have a lot of control over those intermediate nodes. You have, because they're end systems, you can leverage the computational storage. So you can start thinking of putting in functionality like transcoding or priority dropping. So we began with this idea, and really the question that's been driving our research over the last few years is this viable? Can we really do this? What are the issues? Can we expose these issues, address them? How far and real can we make this vision? And our contributions have been, first on the architecture front, we have played a very key role in shaping the community's thinking on multicast, moving away from the IP layer to this sort of. Okay. Oh, sorry. We've designed a couple of overlay multicasting protocols, including Narada, which is one of the first ones. And more interesting, I think, we've explored many conceptual issues with the design of these protocols, rather than the design itself. And we've been building a fully operational broadcasting system, which has been used by over 3,000 users. At the outset, this is joint work. A lot of it was done with my colleague Yang Hua, and with whom I've been working on this right from the start. Sometime in 2002, we decided to build this system, and we managed to excite a lot of other students to join our effort. In this talk, I'm actually going to go through a roughly chronological sequence of how we approach this. I'll talk very briefly about some of the early issues we looked at with this architecture. We then decided to go real, moving away from those paper designs. And that exercise both showed the promise, but also highlighted a few important issues. And recently I've been doing a study of one important issue, and I'll present some results from there. One of the first questions we began asking was, overlays by themselves could be inefficient. They can't be as efficient as the underlying IP multicast. For example, if you look at this figure which I showed you earlier, we have not completely eliminated redundancy. Right? If you see the link between Rutgers and the first router there, you still have two copies of the packet that go through. The second is the overlays, let's say going from Rutgers to Berkeley, you're now going through an intermediate node, so you're potentially increasing the delay involved. So we call these metrics the stress and relative delay penalty, and had initially conducted results examining these quantities. Then the next question is constructing overlays itself. You have to do it in an efficient fashion. To give you a sense of what some of the issues involved are, here is an inefficient overlay, right? Because what you have here is a host behind a modem supporting a child behind a LAN. On the other hand, here's another one which is inefficient. You have everyone organized in a long chain. They're going from Rutgers to the west coast and back to the east coast. Right. The lower one is something which looks reasonably efficient from. So, good.
Given that I don't know anything about IP or multicast for that matter, so what are the orders of delays that we're talking about here? So when you said, sort of define this, this notion of stress. So just to get a feel for it.
So if you look at typical delays in the internet today, maybe like within North America, might be like 30, 40 milliseconds, or 15, right? So when we talk of an overlay approach, we found that the penalties you might induce could be a factor of 3 or 4, but they're more significant when the nodes are close to each other to begin with. So it's harder to, you might have a higher penalty, but the absolute delay may be small, right? And with the overlays, you might start seeing delays of 200, 250 milliseconds and so on. And finally, recently we moved more to emphasize broadcasting applications. So this delay metric has actually become even more secondary because it is live, but it's not completely interactive.
I have a question. So in your definition of overlay, you preclude putting overlay devices at strategic locations in the network. I mean, what is the definition?
It's a great question. So I think the question here is, what is an end system really, right? So are we talking about what are these nodes? Are these the actual client machines or the others? Initially we began with a more generic notion, right? So we included any sort of, so something like Akamai, which puts some very dedicated infrastructure outside, would be included in our overlay notion. Over time, we have begun to emphasize this application endpoint model because the idea is it becomes a very low budget, and it's something which it's very hard for Sigcomm, for example, to go to Akamai, right? Now, having said that, there are many in-between models you can think of which are very interesting. So, in fact, in our deployment, we kind of use an intermediate model where we leverage better machines if they exist for the resources, but we don't depend on them. But I think the general goal is let's push it as far as we can to the endpoints. But these are possible deployment alternatives. Okay. The other aspect is you have to deal with dynamics. So you can have a node that fails, you can have a condition on the internet. My apologies, I've shifted the figure here for various reasons. But I'm going to walk you through some very high-level example of what kind of issues these things deal with or what happens, right? This is not a specific protocol, but just a sense of what's going on. So the main notion here is the notion of self-improvement. It's a distributed heuristics. There's no node with global knowledge. So let's say you have a node in the US join the source. It may now get a subset of machines in the group. Having done this, it might make an initial choice which could be bad, right? So US has chosen a node in Asia instead, and it attaches itself there. At some later point, this node could sort of, because it sees its performance is bad, it could probe other nodes that are around and make a wiser decision, right? And this sort of thing happens over time. Like, maybe at some data point, this node fails, and this kind of process repeats. So this is the high-level idea of what's going on in these protocols.
So you tell us what a wiser decision is?
Pardon?
You say, oh, make a wiser decision.
Right.
So you'll tell us what defines wiser.
Yeah, so I'm actually not going to go too much into the talk on that, but I can give you an overview of some of the issues, right? So maybe let me go through this slide, then we can. So some of the issues that come up are, group management. First, how does a member know other members? You need some kind of distributed algorithms to maintain this in a continuous fashion. The second is what kind of metrics do you use in adaptation, and this might be related to what you're saying. Initially, we began with a delay-based metric, but then we moved on to bandwidth, and on the available bandwidth of cards, and on the internet, this doesn't exactly map onto delay. Right. The next issue is actually finding bandwidth is kind of hard because you actually need to have a TCP throughput to measure it. So we looked at some lightweight probing techniques to find this, and what we found was a mixture of like delay-based probing techniques and something which measures the bottleneck bandwidth of hosts. They're very useful in making that sort of cutting the rather than making a random choice. This was a good thing to do. Okay, and apart from that, there are many practical issues that we've addressed, like there are hosts that are constrained for whom no choice of parent is good. maybe he's, for example, a dial-up, right, and just switching parents doesn't get you anywhere. Then we've looked at issues with variable bitrate streams. But I can talk more offline in greater detail. For this talk, I'm going to go on. Yeah. Okay. So, much of our early work sort of demonstrated the potential of this architecture for simulations and internet test beds. But it was very clear to us there were a lot of things that we had not addressed, a lot of things to think about further. If we started working on this on pen and paper, this was actually a very huge design space, and there could potentially be many issues that one had to think about. And in fact, the community had already started thinking of many questions like scaling, redundancy of these structures, and so on. So the path we took instead was, let's build a real system and deploy it, and let that experience guide us to address the first order issues, the first order barriers. Right? And our objective was such a tool could sort of both be useful to the community and help validate the concept. At the same time, it could also guide us along some of the more key issues that need to be handled. To give you a sense of the effort we put into this to make it real, here's a snapshot of what a receiver, what a client sees. Right? So we have supported our system with QuickTime, popular media player, popular platforms like Windows, because I want a layman to be able to use the system. Right? It's a very simple two-click interface to tune in. And we've also built a complete publishing toolkit. So I can give it out and someone can run a broadcast on his own, and here's some of the monitoring infrastructure that the person can see. So we have broadcast over 20 events and had over 200 operational hours. Both 3,600 users, and recently there have been 4 publishers who have actually taken our system and started using it. One of the things was it was not easy to find early adopters of this technology, and it was difficult to get access to non-technical content given our research group orientation. Right? So typically we contacted conferences and lectures, and some of the prominent ones here have included the Sigcomm and SOSP, which are, for those of you not in the field, they are prominent conferences in networking and operating systems. Right? Here, for example, the Sigcomm conference, there were about 380 users in all, with the peak size, that is how many simultaneously used the system, was about 83. So we thought about how we could go further, right, and get more real experience. So we actually did an experimental broadcast /cut.
So just out of curiosity, when you did Sigcomm, is it people who weren't at Sigcomm who were like viewing presentations through the network?
Yes.
Is that what it was?
Yes, and I'll show you some of the participation diversity shortly. So /cut is actually a site for kind of the geeks, if you will, who are for the industry or the like universities. And we just said, here's a new technology, try it. And we had about 1,600 people who tuned in with a peak size of 160 members. Now, to give you a sense of how diverse our participation was, here is the breakdown for the Sigcomm conference. Right? So this is showing you a bar with what fraction of people in different regions. You see a lot of them in North America, but also quite a few in Europe and Asia as well. Okay. And this is measured by where these people were located. Again, a lot of university machines behind well-connected machines, but there were also a bunch of cable and DSL ports in this. If you look at /cut on the other hand, a much more diverse setting, a lot more people behind cable and DSL, and there were lots of people behind hosts like NAT. And this is the thing I would probably zoom into a little later in this talk. Here's a snapshot of the tree we constructed during Sigcomm. Right? So here are the participating machines. The color code represents which geographical region they were in. You can see all these guys were, so it was optimized for bandwidth, but delay was like a secondary metric. You can see that all these hosts were in the West Coast, the bunch of hosts in Europe, they're clustered together and so on. Right? How about the performance? In the conference lecture style applications, it was typically good. Now, for example, in the Sigcomm broadcast, we found 90% of the receivers got at least 90% of the source rate on average. The people who couldn't were typically constrained, like hosts in Asia or behind wireless who couldn't support the source rate to begin with. Right? And we also, most of the responses were also pretty positive. With Slashdot, on the other hand, the performance is not as good. We had only 60% of the receivers see 90% of the source rate. So it is clear that this is the aspect I'm going to go into further, right? But what did we get out of the deployment overall? I think there were many positives. We had demonstrated the value of the application, the potential of this architecture, right? And it seemed like we had some real applications we could already deploy. On the other hand, we also had an issue highlighted, which was this performance under harsher environments. Now, in the rest of the talk, I'm going to look into how we can kind of abstract out this environment. Can we capture this environment in using some index? I'm going to define a framework by which I can analyze some of the protocols that have been proposed. And I'll sort of demonstrate the potential of the solution that can address these issues. Okay. The first question is, how do you summarize the complexity of the internet? If you think of the internet today, you have diverse connections of hosts. You have hosts behind NAT which cannot talk with each other. More complicated, you have hosts who's like there's a node in Europe who might be a good parent to another node in Europe but not to a node in the US. Right? And to add to all this, it can be dynamic. So to capture all this with one metric is actually extremely hard. So we actually took a simpler approach, which is we capture only the outgoing bandwidth of hosts. Right? So if you think about a DSL, maybe the outgoing bandwidth is 100 kbps. A T1 maybe 1.5 Mbps, so on. Okay? And we consider the average outgoing bandwidth taken across all the hosts, normalized to source rate, and this defines the resource index. Now, to build a feasible tree, your resource index must be at least 1. Right? If you take a case where everyone is behind a DSL or dial-up, it's probably infeasible to construct a tree. But at the same time, you should remember this is an upper bound because we have not incorporated the quality notions in it.
How does this take care of the case where the previous slide you showed 2 in Europe and 1 in
Yeah, it does not. So that's why I call this an upper bound. To actually take care of things like, I'm just trying to tell you the internet is so complex that if you want to model all these, it's very hard. So the approach is, let's take something simple, but which could be give you a lot of intuition at the same time. Now, what we could do is we were able to extend this to consider NATs using a little more complication, which I won't go into in this talk. Right? But whenever you use that metric, you'll remember it's an upper bound.
So if everybody in the world is a dial-up, then your index will be less than or equal to 1?
Yeah.
How do you know that you're a dial-up? How do you measure? Suppose I gave you AOL,
okay,
and all my customers are dial-up.
Yeah.
How would you come up with this result?
Okay, so this is more for an offline analysis.
So you don't.
Yeah. I've moved on to sort of modeling. I'm trying to model something and sort of evaluate it in the work. Okay. To model the outgoing bandwidth, look at the typical application bit rates we use with like 300 to 400 kbps, and we sort of assign a degree to each node. So maybe the DSL nodes have a degree of 0. The T1 nodes we give it a degree of 2, and the T3 nodes a degree of 10. And this neglects aspects like multi-homing, which might exist. So using this model, the resource index for Sigcomm is 7.64. And this is kind of the distribution of hosts that you have. And for Slashdot it's 2.28. So this kind of gives you a good notion that you're dealing with a harsher environment.
Question. So somebody behind that, would you assign them 0? They cannot basically host.
So in this talk I'm going to neglect the constraints imposed by NAT. Now the way we did that computation for the metric with NATs, it would actually push this number further down. Right?
So less number of Ethernet means for you it's cobs.
Yeah.
Because basically you don't have any shared value.
Right.
So the tree will not be that efficient.
Yeah.
But is it switched Ethernet or shared Ethernet? What if everybody is switched Ethernet?
Oh, again, that is one aspect. So this is, I've actually moved on to try and model a problem, and right. So I've again neglected that aspect in this model.
Because the world is moving towards more and more switched Ethernet, so you very rarely get one node sharing a lot of children.
On the other hand, it's not clear you'll have many nodes part of the group behind the same sharing.
Okay.
Right? So, desirable host protocols. First is you want to honor per node constraints. The second is these degree constraints are heterogeneous. The third is you should be able to accommodate all these receivers if the resource index is greater than or equal to 1. And you want to have good performance even if this index is low. So, here's a taxonomy of some of the protocol proposals in literature. Right? On the one hand, you have performance-centric protocols, which is where we fall. And the idea here is you directly optimize your overlay for the particular application you have in mind. On the other hand, there are DHT-based protocols that are being proposed. And the notion here is you build a more generic abstraction that could be applied for a wide range of applications, but arguably at modest cost for each application. So in this work, or today I'm just going to talk about the performance-centric protocols, but there are some interesting implications for these kind of constraints for this DHT-based system. We can talk about it. So when I analyze some of these most popular or well-cited protocols, the key thing is they do not distinguish between capabilities of nodes in the construction of trees, and they are not evaluated under the framework we consider this low resource index and heterogeneity. Right? And there are protocols that do not honor the per node degree constraints, like overcast and lice. And there are some subtle issues that come up if you have degree constraints. So what happens? Right? So with heterogeneous constraints, so here is, let's say, a tree that we have, and the fat nodes represent nodes with higher bandwidth capability. The thin nodes are those with lower capability. Let's say a node dies, and you could have a situation where a node such as this may join the parent, right? And you are kind of disconnected at this point. Now, what has happened is the tree has reached suboptimal configurations. Like even though this core, even though the set of participants has the capacity to support children, you have not, you're not able to utilize the resources here, right? Okay, so you're not differentiating between the capabilities of nodes, like all these protocols. And what happens is, let's say these guys cannot take any children, right? So you have this core which has become saturated now.
Assuming that you have an alternate path from this small guy.
Yeah, so what you really wanted was for this guy to hook on here. Right? The second aspect about these heterogeneous constraints is your tree depth may increase, right? And you could have a higher frequency of interrupts now, because if you have a tree with a higher depth, a node lower down could be affected by more nodes and links, failures. And under some approximations, you can show that loss is at least like proportional to the depth.
So, going back to your previous picture,
Yeah.
why would the fat node not be able to connect up in an overlay situation? Anyone can connect to anyone.
Oh, that's because I have this notion of a degree constraint in this model.
You didn't define that yet.
Yeah, this is what maybe I went too fast. So the model is, let's assign a degree to each node, which captures the capacity of that node, right? And I'm also capturing the overall resource of the environment.
So, explain which degree was that fat node in
Oh,
your picture?
sorry. So here, let's assume that for convenience, let's assume that just degree 10 and degree 0. Okay? And these are all degree 0, the fat ones are degree 10.
I can't go through degree 0 now.
Yeah. So you have 2 degree 0 nodes attached to this, maybe the source, right? And
Degree 10 cannot
But
be
the other one wasn't connected to it. Why do you allow the degree 0 to get in and not the other guy?
okay, that is the key, right? So that aspect has been neglected in the community,
By
which is
whom?
this notion.
By everyone or a particular protocol?
In general, the notion of heterogeneous degree capabilities hasn't been analyzed. A lot of work has been put into path characteristics.
Okay, so you're saying they will just pick the node with the preferred path, but not necessarily with the capacity.
Right.
Support.
So I think the big picture here is, look, this is, it turns out there's a lot of emphasis put on path. You do some of the deployment, this sort of thing strikes you in the face as being more critical. And after you see it, some of the things, it seems obvious you should do this, but really they should have been first order principles in your design. I think that's kind of the thread I'm arguing. Okay? Now here, on the other hand, let's say you have a mix of degree 10 and degree 2 nodes and degree 0 nodes. Now it becomes more interesting because your depth can increase, right? And a node low down could see more interrupts because of the higher depth. Okay.
So sort of the goal is to have as shallow a tree as possible, right?
Right. So ideally you want to construct a tree with low
Very
depth.
little depth, right?
Right.
Isn't it always better to put the fattest nodes up at the top?
But it may not be possible.
But the question is, how do you do it? Right?
Okay. Well,
Okay, I think there are two things here. The first is just exposing the problem through sort of deployment, right? Which is, you keep thinking of a lot of things like congestion, like delay, RDP, and so on. But and this is the path which we have gone through as a community as a whole. But this aspect, the fact that there are heterogeneous nodes becomes much more dominant, right? Now, after you do this, you start asking these questions. Shouldn't I put the fatter nodes on top and so on? And then you could ask questions like, you could look at some simple techniques to achieve it. Just what this, and I'm also trying to systematically see in what regimes these techniques are more critical.
And also, if you are going to deploy it on an already deployed network, how will you be able to move the fat nodes and
Yeah, we need to cause some disruption, which I'm going to discuss.
when Bobby says an already deployed network, what does he mean? You mean like a tree that's already set up?
Maybe it's already giving video as well. Okay.
So what your concern most is about the bandwidth. So you define the fat node as with high capacity
Right.
based on bandwidth. So you don't concern about the delay. If this fat node is physically located far away, so the delay with those two fat nodes are really long, you will still consider that thing.
Okay, I think the question here is, when if you consider only node capabilities, in general, for example, there could be a host say in Taiwan, which is extremely powerful, but the delay is, but performance from there to all the other hosts is not good, right? Now, yeah, so these sort of things would complicate the deployment in practice, and I haven't actually implemented these notions, but they are some of the things which make it more difficult when you go from here to real deployment.
Can the degree metric include some component of this?
What I would do is maybe I would have some kind of heuristics by which I can learn the performance of the nodes, have some notion of the quality of the nodes. That's currently what I'm doing actually. And you sort of learn this quality online, right? And maybe initially this node doesn't have much, I mean, you treat it as a low category, but over time it sort of gets better promoted and can do some of this stuff.
And this learning will be what, distributed?
Yeah. Now that's some stuff which I'm doing right now. Okay, but this is, I think, to again, I think the bigger picture is highlighting the importance of this issue. Okay. Now,
so I had a follow-up question. So on, when you say you have node quality in some way, isn't link quality not necessarily the same? You know, when you look at a fat node in Taiwan, talking to a fat node in the US, the link quality could be poor because of TCP retransmission delays, for example. Or there might be a gateway somewhere in the middle which is a bottleneck. So how do you assess that problem without looking at pairwise link quality as well?
right. So I have actually not. This is actually part of my ongoing work to look at some of the heuristics for this. Now, I think if you want to build a practical implementation there, you would sort of, you could look at some gross properties like overall, like just maybe that it would work out that there would be more hosts in North America, fewer hosts in Taiwan, and you sort of online learn when people have chosen Taiwan experience what the performance was.
Yeah, I understand, but I was thinking that ought to be a first order consideration rather than added on later. I can see the node metric has some value, but the link metric ought to be considered also in the basic formulation, I would think. Because if you have some bottleneck in the middle which drops your throughput to 50 kilobits, what do? You don't know anything about it. You just know that each node can put out quite a lot.
That's true, okay, but see again, the aspect is these things can be considered as we go along, right? But and in fact there are even more interesting things. For example, we have seen that there are nodes which could be misconfigured. Something like a DSL which advertises itself to be an Ethernet, right? Which is the opposite of preloading problem.
So that gets to second order effects. I'm still looking at first order metrics that seem to be important.
I would also argue about another aspect is, you see, if you again do this on pen and paper, right? These sort of things again seem like they have to be. There'll be a lot of such things you have to consider. The next may be the multi-homing aspect, right? But part of this is really showing you some of the complexity in the field itself, which is why you needed that deployment to guide you to what were the earlier questions, what were the some of the critical questions. In fact, what I'll also show you in these results is even the simple notion of preemption, it becomes critical only in some regimes.
So anyway, let you continue and I'll take it up at the end.
Okay. Okay. So there are two things we did here in our evaluation. We varied the resource index and we varied the constitution of hosts for the same resource index. Right? So for example, if you have a resource index 2, you could imagine all your nodes are behind T1, or you could have 20% behind T3 and 80% behind T2, so on. Right? Now, the methodology here was to assume a uniform network delay model because we are dealing with bandwidth sensitive applications. the group dynamic pattern was a Poisson arrival and Pareto state time, and this modeling sort of things we've seen in deployment. And the metrics here were the rejection and the disconnection time. So the rejection is, because you may have suboptimal configurations and node cannot hook back on to a parent. And the disconnection fraction gives you what fraction of time you didn't get data. And here I assume the node hasn't been able to hook on to anyone for 30 seconds, it quits. Okay, so in this graph, the x-axis shows you the resource index, and I'm assuming in this graph I fixed the non-contributors to be 50%. Okay, and I'm looking at the rejection rates. Now what you see is it really gets bad as your resource index becomes low. Right? Whereas over here, where the overall resource was high, it was not as critical. Like you don't see much rejection. The other aspect is you see a lot of variance here, which is because these sort of suboptimalities are very sensitive to the particular run. I think this also offers some insight on why we didn't see these issues in an earlier deployment. Like though, for example, Sigcomm had 20% of the host behind DSL, and it seems natural to do this kind of thing there too. The notion is it's really in this regime that it becomes more critical. Right? The next aspect is what happens if I fix the resource index and vary the fraction of non-contributors. I'm changing the constitution. So in this graph, in the x-axis, the fraction of non-contributors. As I move to the right, I have more hosts behind which are degree 0 and degree 10, but fewer nodes which are behind T1. Right?
So RI is the number of sort of outgoing connections between.
Yeah, so I think it's really will boil down to something like the average of the degrees of the nodes. That's
so it's the average, but it's one number, global number for the whole population. You take all of the, so there's an RI for each node, or
no, it's global for the system, which is capturing the resource of the entire system.
So when you say, oh, it's 2.28, but you vary the non-contributors.
Yeah.
The non-contributors are people whose RI is less, 1 or less.
No, so the RI is just a system-wide concept, right? Now, your RI is defined by the composition of your constituents.
Say that again?
Your RI would be defined by your constitution of component.
Right.
So let's suppose, so if, for example, I had 50%. With these approximations, if it turns out to be the average degree, right? If you have 50% degree 0 and 50% degree 10, the RI is going to be 5.
Okay, so when you do this thing where you fix RI, but you vary the population, it means like somehow the fat nodes are getting really fat.
Okay, so let's take a simple example. Let's say RI is 2 and we vary the constitution.
Yeah.
If I have if I have the fraction of non-contributors as 0, it's a completely homogeneous environment.
Right, and they're all 2.
All 2. As I'm increasing the fraction of non-contributors, I'm increasing the fat nodes and the non-contributors, and it's becoming more like for the same resource index, there's more heterogeneity in the system. Okay. So the point I want to make is, it's as you increase the heterogeneity, again you see a higher rejection rate. So it's the combination of the average. It's also it's a high resource, low resource and high heterogeneity regime that this problem is the most critical, which is what maps onto the current environment, the application environment.
I would have thought of it sort of the other way. I mean, I would have thought the situation over here at the right, you've got a fairly small number of big fat nodes, right?
Right.
Right, and a lot of people who are just listening, right? It's sort of like you've got a collection of sort of powerful machines who then serve lots of people. And I would have thought then you'd have...
Yeah, but it's still 228.
Yeah,
So,
but I would
no,
have
actually, what-
getting a couple really powerful guys to give a shallow tree where the powerful guys serve lots of
But
people.
they're also going to send high bandwidth out.
Oh, that's
Actually,
Smaller
maybe
ones cannot take it.
maybe I should get your question again. So what is your, or maybe we can take.
I guess I didn't have a question as much as I think the results is surprising.
So here's what's happening, right? As I move to the right, I'm increasing the number of high degree nodes and the fraction of non-contributors, becoming more heterogeneous. And I'm not doing differential treatment, right? This is analyzing the impact without differential treatment. So this criticality of the thing becomes more critical as there's more heterogeneity. Okay. The other graph is showing you that for the same amount of heterogeneity, for the same number of low degree nodes, the problem is again becoming critical as I make that environment more resource poor. Okay. Now, here's a potential way to address this, right? Which is the key principle is this notion of differential contributions, and you have the idea that a larger contributor should be able to displace a smaller one. Okay. Now, I've considered two variants of this. Preempt 0, where a contributor, whether degree 10 or degree 0, can preempt a non-contributor alone. This preempt degree is a more general notion where you're allowing a high or a higher degree node to preempt a lower degree node. Okay. Now, here's just an example to see how this may work. So, let's say you have a situation like this. Okay, so this node is looking for a new parent. It can displace that subtree, and the subtree comes on and hooks onto a lower node a little later. This is how a preemption scheme would work. Right? So the idea is you have this fat node sort of looking for a parent, right? And it sort of kicks out the subtree with a thin node on top, and the thin node sort of now hunts for a new parent which goes here. This is kind of what you need to do to make the tree balanced. Right?
Are you talking about the recovery situation or the first setup?
I see. So okay. So the question is, when is this preemption happening? When a node joins, or this would actually, the way I do this is it happens every time a node is looking for a new parent. Either is a new node that's joining, or his parent is disconnected and is reconnected.
And preemption, you're doing just connecting. Process of connecting.
Preemption means when I look for a new parent, I have the capacity to kick out an existing thread. So the normal optimization is non-preemptive in the sense when I look for a new parent, I just attach myself to someone if he has spare capacity. But here I'm going further and adding in this dimension, I can kick out something.
After this configuration, if that small guy leaves the group, where will I go? This
Which small guy?
This guy.
This one.
Next one.
This one.
No. So this is a new configuration, right?
Right.
So now suppose his grandparent leaves the group. This small cluster you have.
This.
No, the one below. Yeah.
Okay.
Now if that guy leaves, what should happen?
Okay, this guy leaves. What could happen is both these guys are trying to reconnect. Right? Now, let's say I've abstracted out the protocol detail. Let's say in the protocol, this guy, the nodes try to attach to the grandparent. Right? What would happen is maybe the way things work, this node may attach himself here first. But then, shortly after, when this guy tries to contact the same grandparent, he would displace this node, and this node would search around. Now, one question you may ask is, couldn't this guy just reconnect to this node? But the problem is this node may be saturated.
So what I'm trying to say, does your protocol worry about stability issues? Or this whole, from the time topology change occurs to the time you settle to your, according to your RI, the network, how are you giving any consideration to sort of delay this attach in the hope that you're getting a much balanced tree, or is it like greedy?
This is right now it's greedy. See, again, I think this work is not a synthesis work as much as highlighting the principal aspect of it. Okay. But I think these are great questions in a synthesis point of view, which maybe we can, some of which Ray also raised. Okay. Now the question is preemption worth it? Right? Now the benefit is, it helps you recover from these suboptimal configurations. And it also helps increase the stability because, yeah.
In terms of costs, I mean, you're sort of saying that every node can have the throughput that, however powerful it is, but you're also having an underlying assumption that you can get that throughput as you wish. There's no notion of cost, probably,
Yeah, that's what Jay was asking.
Yeah, I think it's related to that.
Yeah, right.
So again, that's that aspect I'm currently looking at. It's more, I haven't looked at the synthesis aspect of this issue.
What I'm saying is that it can be included in your
In my model.
Yeah.
It could, definitely. But maybe we should discuss this after I finish this. Okay? Now, it helps you recover from the suboptimal configurations, but it also, by lowering the depth, it has improved the stability, right? But on the other hand, you're causing these disruptions which could increase the instability in the first place, right? And you're also potentially penalizing the performance of the lowest class of hosts. So there are fairness concerns that will consider. So to look at this, I looked at two metrics. One was the interrupt rate that hosts see, and the fraction of time a host is disconnected. Now, the way to summarize this is I would look at the average interrupt rate of a host throughout the session, and then across the host I would take the median. I've also taken higher percentiles, but I'm not showing that today. Okay. Now, this is these are the results for one particular configuration, right, which is the resource index is 2.28, but 50% non-contributors. Okay. Now, what you find here is with the most general form of preemption. Okay, the x-axis here, the y-axis here is the interrupt rate, the median of the interrupt rates across receivers, measured in number of interrupts per second. Okay. Now, what you see is the preempt degree is actually doing much better in terms of interrupt rates than preempt 0 or the no preemption, which means the more general form of preemption, the cost of disruptions actually seems small compared to compared to the benefits of lowering depth. Right. Now, here's some intuition for why this is so. If you think of the tree that the preemption causes, it's essentially you have some fat nodes on the top and thinner nodes lower down, right? Now, what the preemption, most of these preemptions, there are two cases that may occur. In the one hand, you could have a small fraction of the fat nodes. On the other, and in that case, what happens is there are very few preemptions in the first place. But if you have a lot of fat nodes, then you have a top level core of fat nodes, and your preemptions are occurring low in the tree. So you're affecting very few people with each preemption. Now here is, so given that the interrupt rate goes down, here is the effect on the disconnection time. And you can see again, it's being brought down. Now I've actually done a lot of sensitivity analysis on this sort of thing. And like, it's obviously sensitive to the heterogeneity model, like what kind of degree assignments and so on. So I think what would work is, this sort of preemption becomes more critical as the disparity between the classes is higher. And I think for current internet settings, the 3-class model is probably good enough. I've also looked at some sensitivity with the scale of the participation, and again, this becomes more critical. important as the scale is also large. Okay. Now, there are two directions that we're doing in ongoing work. First is, I think a lot of questions have brought it up here, which is the practical considerations. And the way I'm trying to do this is use some online algorithms to determine the quality of a host. And you use this to damp some of the preemptions, right? And actually there are other aspects you have to consider. There could be unstable nodes that stay for a very short while, but claim they have a high degree. Now you have to damp some of this in your preemption scheme. And the misconfigured nodes, which the point which I mentioned earlier, the DSLs advertising themselves as Ethernet. Okay. The other aspect is I've looked at what these results mean for the DHT style protocols. Now here, for those of you not familiar with it, it's actually what these protocols do is they build an ID space, logical ID space, which has no relation to the network topology, right? And then they try to add some heuristics to construct the tree. But one important implication of this is now your ID space has to be correlated with the node capabilities. And there's also some other stuff I can talk offline if you're working in this field. Basically, I've tried to say what are the trade-offs between a DHT approach and a performance-centric approach. And I think we have a metric which could be interesting in shedding some light on this. Okay, so here's move to the related work. So Sigmetric's paper was one of the earliest on overlay multicast. Since then, there's been significant effort shortly after this, including Lloyd, Scattercast, and Overcast. Right? And since then, this field has actually evolved into one in its own right. Some of the metrics we propose expressed in RGP have become standard benchmarks. A lot of works have compared themselves with Narada, which was one of our protocols. At the architecture level, Scattercast and Overcast are purely infrastructure-centric overlays. Right? That is, they are closer to the Akamai notion. Now, we have actually a more application endpoint based, but we are also exploring a hybrid where you can dynamically recruit services of nodes that may be available. More recently, there was a proposal called IP Multicast, which is again hybrid, but here the data forwarding is still done by the infrastructure level. All the heuristics we've seen have really dealt with the centralized, distributed algorithms. There's been work like KubeNet and ALMI, which have been more of a centralized approach. There's been a lot of protocol design work in the community. I'm not able to go into it for time constraints, but broadly, the community has been focusing on reducing group management overhead for scaling and on redundancy in data delivery. Okay? And my focus has been more on issues related to bandwidth adaptation and this heterogeneous constraint. There is one particularly interesting idea here is there's a recent paper on SOSP which has this notion of multiple trees. So instead of delivering data on one tree, you construct K trees and use an MDC coding algorithm to sort of send. So you take a source, you encode it into K streams using MDC. You construct K trees and you send each stream along one tree, right? And the benefit here is you have better resiliency. And what they've also explored is you have an interior, each node is an interior node in exactly one tree, right? Now, why that work is that interesting is because it's in a way by which even in more extreme environments like all cable modem, you can potentially use this kind of solution to extend this overlay multicast. And another interesting aspect is when you go to the multi-tree model, it's also an example where you're creating heterogeneity out of an existing homogeneous setting. So this sort of work like preemption becomes critical there.
So who did this work?
So there are two works actually. One was at Microsoft Research by Venkat Padmanabhan, and the other was again at Microsoft but Cambridge. It's called Slipstream. It was at SOSP last year. So some of this has really been like say around early last year is when it got published in SOSP last October.
I thought the multimedia community, MVCs and using multiple trees has been something that has been done for at least a few years now.
I see. Then maybe the novelty is applying it to this particular domain. And again, what it's highlighting is that flexibility with this overlay-based approach to multicast, because you can now do some. You can really make it very tied to your routing algorithm, tree construction algorithm. So that's it's a rich space for exploration. Okay, I'll begin to wrap up. So the goal here is to build to ubiquitously deploy conferencing and broadcasting applications. For a lot of the 1990s, the community was investigating this using the IP Multicast architecture. We've been one of the earliest advocates for the end system approach, and our research has really been how far and real can we make this idea. Right? As part of this effort, we built an operational prototype used by over 3,000 people. It's both proving a useful tool to the community and guiding some of our future research.